Okay, good morning. You may notice from after middle term exam, we gave 2 weeks deadline for all assignment, and the reason is we also arrange a tutorial, only discuss assignment related questions, and then usually the TA will pick one of the questions from assignment and explain in details and help us to digest and then to complete assignment by ourselves. I said after middle term, if you understand every questions in assignment and then by doing them by yourself, and then you should get at least 80% in the final exam, right? And sorry. Okay, right now some questions about very detailed problem. You ask detailed problems after my class, okay, or we can find another time. So I have my agenda for today's class. I have to fulfill this part first. Okay, if you interrupt me questions regarding what we are discussing, very welcome, right? And also to read yours, I have to put my glasses. All right, and so pay your effort on assignment and also attend tutorials as much as possible. Okay, I slowed down the discussion on this transmission line part because it is so important. Okay, I don't like go too fast and then you skip all those basic concepts and then basically waste both your time and my time. And let's continue. This page, I stay on this page. Okay, first, let's have a quick review. Those are very important concepts about transmission line. The difference between transmission line and the ordinary circuit is we are talking about, okay, in transmission line, the dimensions of the circuit matters, okay? So that means, you see, we have to consider the time delay, okay, the time delay of the signal propagating down the transmission line. But however, in ordinary circuit, we don't need to, okay? You see, because frequency is too low, the wavelength is too long, and then your circuit size compared to wavelength is negligible. But for transmission line, it's not, okay? Transmission line, the length compared to the wavelength is comparable, okay? It's a fractional. So that's why we have to consider the dimensions of transmission line. Then for in general, a transmission line we can represent by such a circuit model, okay? This, even though this is the total length, so very short. Oh, I forgot my glove. So this, even though I put many segments of this LC, but this is still very small, very short distance, okay, length of transmission line. So we use infinite number of small sections, okay, infinite number of small sections. So LC, right? So this L is inductance per unit length, and C is capacitance per unit length. So per unit length, okay, L and C, okay. So that means the total capacitance depend on the length, right? Depend on the length. So if for a given length, then you can find equivalent inductance and capacitance and so on. Okay, so this is one of the basic concepts we already introduced. Okay, so this is concept one or basic principle. Okay, then we also mentioned the voltage and the current down the transmission line also tend to be a wave in nature. Okay, so that means voltage is a wave that propagating in positive z direction and negative z direction, right? So we use the positive and negative z directions. Okay, same as current. Current has a positive and negative. So when the wave propagating in one direction, any of this is traveling wave. Okay, this traveling wave, this is also traveling wave. Okay, because it's propagating in one direction. Okay, but when you combine the two together, not traveling wave, right? We call that is a standing wave. Okay, so this is a basic principle two, right? So the voltage and the current down the transmission line also waves and propagated in two directions, because for giving a wire transmission line, you only can propagate in one direction, right? The basic principle three is voltage and the current for traveling wave, the ratio is constant. This constant, the Z sub 0 we call characteristic impedance. Maybe some may wondering why we call impedance, why not call resistance? Okay. Because in general, this quantity could be complex if you have a loss. Okay, if you have a loss. So if you have a loss, this could be a complex number and then also frequency dependent. So that's why we call impedance. But we keep the problem simple. In our initial discussion, we assume it is a real. Okay, it is a real, because this for transmission line, this can be proved. It is equal to square root of L over C. Right. And the important thing is only for traveling wave, we can take a ratio voltage and current to obtain characteristic impedance. That is defined for positive direction wave. But for negative direction traveling wave, we use another equation. The only difference is the minus sign, right? Only difference is the minus sign. So when you add current propagating in two directions or voltage propagating in two directions, we get total voltage or total current. Okay, that in general is a standing wave. This is a very important three basic property of transmission line. One little thing is a transmission line. We describe a transmission line using one is characteristic impedance and another is a propagation constant or wave speed, right? Wave's speed we call VP or phase velocity, right? We'll use this. So this is what we have discussed. Now we are addressing our simplest problem first. We consider a transmission line with a certain length the length is L with certain length, but we put a termination, simplest termination, real termination, which is resistive. And tomorrow we will discuss if we put a reactive component, say L and C, what happened, right? So in this case, if we have a step voltage, okay, we call step voltage. How to create step voltage is we have this switch turned on, okay? So that means our voltage with time is at t equal to 0, turned on, and then constant, right? So this is V0, right? This is V0. So we call such a function, we call step function, right? But how about this? This is also step function. It's just say I turned it on at t equal to t0, right? So this is still step response, right? Or step excitation, okay, at beginning. What our objective is, what happened down the transmission line for the voltage and current, right? And at a different location or at a different time, right? So we use this very basic result gradually build up to help us to analyze more complex things, right? Okay. So at the beginning, why it turned on? So this step response just hit on this transmission line. We haven't now long enough time for this step to reach to the termination. So this wave doesn't know what terminal it will say, right? The only thing it says is it says the resistance, okay, resistance, and with the value of characteristic impedance, okay. This resistance, as if this circuit is connected to such a simple circuit, you only have two resistances. One is internal resistance, okay, of the source, and another is transmission line, okay. This remember, this is after you turn on, okay, at the t equal to 0 instance, okay. This is what you can see. Then we know the voltage built up on the transmission line is initial voltage. The initial voltage is just a voltage divider, right? And what is the initial current? Is initial current, we know this is initial current, right? So it's as simple as this because we are dealing with a simple circuit at t equal to 0, right? Okay, then the wave travels, right? Wave travels for how long? For L distance. At what speed? It's Vp, okay? So how long it takes, the total time it takes t, okay? Or we write this like a capital T, okay? We write like capital T, okay? We spend the capital T, when t equal to capital T, the wave reach to the end of the transmission line, okay? The end. Then at the end, what we have? We have a load, okay? We have a load. So at the load, the wave hit on the load, and you must have a certain reflection, okay? Otherwise, if you use initial voltage if you use initial voltage divided by this load, that were not equal to the initial current. So this is not correct. So it's when it hit on the boundary or hit on the terminal, okay, that reflection occurred immediately, okay? So occurred immediately. So that's why it T equal to T, okay, which is L over Vp, right? So the voltage become V. This is the coming wave, okay, initial wave propagating in positive z direction. I put the plus sign, and then plus reflect wave, okay, then plus reflect wave, and the current is also also this is a total voltage and total current equal to positive directed current plus reflect current, okay? Then the total voltage and the total current satisfy Ohm's law over the terminal, okay? So that is resistance, okay? Okay, according to this relation, okay, substitute what we already learned, the basic property, okay, the basic principle, then we can express the reflect voltage and the reflect current related with the characteristic impedance. Then we left this as an assignment about 2 weeks ago, right? So we can derive this, okay? Have reflection coefficient, this is for voltage, and also we have a current reflection coefficient. The only difference is the minus sign, okay? We have discussed this, right? Now let's continue our discussion. Then this reflected wave traveling back, okay, back to the source. After hit on the source, and then that has a reflection again, right? So I put minus and the plus because reflect and the plus, right? And then reflect and the plus also similarly, we need to satisfy the total KVL equation. What the KVL equation is, this total voltage, okay, this become okay, we have a total voltage. This is total voltage, right? So this is V0 RG. Then we can have a loop equation, right? We can have a loop equation which resolves this. This is a loop equation. Okay, interestingly, we can find out this reflected wave from this terminal. Also, we can define reflection coefficient. This reflection coefficient is looking, you stand in the transmission line, looking at the load, or looking at the source, and after you short circuit source. This is exactly what a Thevenin equivalence tells us. So that's a basic circuit theory. What is equivalence resistance? You're looking into this. Again, the reflection coefficient equal to whatever you see, the resistance minus what you have, right? Where you stand in the transmission line, divided by what you have seen and what you have. Okay, same as this. Okay, what do you see, right? What do you see? What do you see? This is our eyes. Okay, what you see is this, right? This is what you have. Okay, this is what you have. Okay, this is what you have. This is because you're standing in the transmission line. You're standing in the transmission line with characteristic impedance, all right? With characteristic impedance. So now we have also introduced a special case when the terminal is short circuit, reflection coefficient for -1, open circuit +1, infinity. Oh, sorry, open circuit load is infinity, right? If that is equal, what you see equal to what you have, then reflection coefficient is 0. Okay. Now let's officially introduce we call bounce diagram technique. Okay. Right. So let's introduce this very convenient, very common sense method. Okay, help us to discuss the problem. Okay. Now we are looking at the problem also a step response. But what is step response is as is turned on, okay, at t equals to 0, right? T equals to 0 and turned on, right? And then forever, right? Forever. Then you forever you can expect your launch a wave propagating, okay, towards that direction and come back again and come back again, right? So you add up all this. So no matter what, we have initial time. The initial time is when you turn that on. What is initial voltage? The initial voltage is as if this is connected by 60 ohm, right? Then we have a voltage divider. Divide what? Divide this initial battery voltage, 60 ohm, 60 volt. Okay. Initial current is this resistance plus this divided by this is 1 amp, and the reflection coefficient at terminal. This is what is we saying. This is what we have, right? So toward load direction is 1/3. Toward source direction, what you see is 40. What we have is 60, right? 40 minus 60 divided by 40 plus 60 is a minus 1/5. Okay. Now we have ready. To do the analysis. Okay. Now we use this diagram. We know at the load reflection coefficient 1/3 and at source reflection. Now we all talk about the voltage reflection coefficient. Okay. For current reflection coefficient, just add the negative sign. Now what we have is that initial voltage we said 60, right? So the 60 travel. So the 60, okay. So the 60 travel all the way takes how long? Takes capital T equal to L divided by Vp, right? When the time, what is the Vp for this problem? The Vp, okay. Now we use capital T, right? So capital T for one capital T, okay? If the capital T okay, for one capital T, sorry. For one capital T, it travels before you're reaching there, right? So we have this voltage travel all the way. So when the heat on the boundary, reflection coefficient is 1/3, right? So that means 60 multiplied by 1/3, 20. This is a reflected wave. Refracted wave hit on this south side, and then with a reflection coefficient of minus 1/5. Okay, then 20 multiplied by minus 1/5 is a minus 4. Okay, minus 4 still go on, right? Hit on this wall, and then this is already take 1, 2, 3. 3 capital T, right? 3 capital T. And minus 4 multiplied by 1/3 again. This is reflected. So this keep going, right? So this is a multiple reflection. So when you have one wave already hit, so this is already exists. This also exists. So then we can imagine at a certain time, say if this is the time of observation time, and then if you observe everything is here, if you stand here to observe what the total voltage is, you have this add up together. This is your total voltage. You already have. Similarly, you have a current, but for current, the only difference is our initial current, which you have, of course, it's not equal to initial voltage, and the reflection coefficient for current, you have minus sign. We have minus sign, right? The method is the same. Okay, then let's first take a look. We have to quick. Let's take a look at the source. Okay, it's the source. What we have. Okay, it's the source. It is this location. See, is this location. If I'm standing here, okay, what I observe after all the bounce force back and forth, right? So initial voltage is 60, okay. Let's look at the voltage. Sorry. Let's look at the voltage. Okay, so the T goes to infinity. Okay, so it's initial 60. Okay, so I add 60. Then I look at the total voltage going towards that direction, right? So I have 60 goes this direction, minus 4 goes this direction, and plus 4 over 15, and so on, right? So I add all this up. This is a geometric sequence. Okay, geometric sequence, we know at infinity what we have, right? Same as the voltage, total voltage coming back, right? 20 coming back, I use different color. So coming back, right? Then this is this. So this is also geometric sequence. What is the ratio for the geometric sequence? The ratio Q equal to minus 150. Why is it minus 150? That is equal to gamma source multiplied by gamma load. Okay, right? The current is the same. Okay, current is the same. Right. Then if you have a total voltage at the source and the total current at the two terminal after T goes to infinity, it's just a total voltage go toward that direction and minus that direction, right? So this value equal to what? Equal to as if you don't have a transmission line. okay, as if you have battery, you have source impedance, you have a load, you connect it, okay, using ordinary. This is ordinary wire. It's not a transmission line. This is just a voltage divider. Why is this? Of course it is this. Because go back to our circuit model for transmission line, that help us to understand. Okay, our transmission line model is this. Okay, LC, LC, LC. You have initial step. You have initial step. Then this, you have a transit in this part. But after a long time, this become DC, right? This become the transient analysis is already over. We are looking at the steady state. So steady state, the charge on the capacitor already discharged, right? So the voltage doesn't change with time anymore. Therefore, inductance becomes short circuit. Okay, capacitor become open circuit. Okay, become open circuit. So what is this? Just an ordinary circuit wire. Okay, this is a steady state. So that means when we look at this problem, no matter what, it's a steady state. You consider is your transmission line become ordinary circuit. Okay, become ordinary circuit. This is because voltage and current doesn't change with time anymore. Okay, doesn't change with time anymore. So the steady state. Now let's look at the no steady state. Okay, we call transient analysis. Okay, let's look at. This is more important because when we send the digital circuit, okay, so this is all chance. Okay, we don't have such problems. When you turn it on, you don't care. Then you go home to sleep, right? And then when you come back to see what voltage is, nobody interested. We just couldn't wait because we are using high speed data, right? So after we launch one bit, and then we immediately will launch another bit and another bit, right? So this is we are interested in the transient analysis. When we do the transient analysis, still this problem, okay? Now let's look at the voltage. Let's look at the voltage. Voltage at, for example, the voltage at Z equal to 0. Okay. When voltage equal to Z equal to 0, at the beginning, initial voltage, you haven't received any reflect signal at your source yet, right? So you have 60, right? So we have a 60. We have a 60. Okay, we have 60. So once the time spent 1t, okay, this is a time. This is time. Okay, this is also time. Okay, so this is, you see the time, this is 0, this is 1, this is 3. T, capital T, right? The unit is a total time it travel from one end to another end. So after 1t and 2t, right? 2t, you receive a reflected wave. Okay, you receive reflected wave. This reflected wave, but because it's so quick, when it hit on this boundary and the reflection, right? Okay, it happened in the same time. So that's why I draw this dashed line, okay, to emphasize, okay, let me magnify this, okay. This is a source, z equal to 0, okay. Then I magnify this. I use the dashed line. This distance, delta, is approach to 0, okay. Then that means when I have reflect a wave and then this happen immediately in the same time, okay. It happened at the same time. So that's why you see this is a v minus, this is a v minus plus, okay. These two things happen in the same time, so I have to consider them together, okay. I have to consider them together. So this is how I consider them together is I have one is this is equal to this is equal to 20, then this is equal to minus 4, right? So I have to consider them together. So that is 16, right? That is 16. 16 plus original 60, so that is 76. Okay, this is how we got 76, right? So after another 2t, after another 2t, I have another 2 wave. One is this, one is this. I have to add together, right? And these two have to be combined, okay? So these two has to be combined, okay? Has to be combined. So you add these two, that become this, and so on. So the trick is, okay, you're counting the time. That is easy. Everybody, even the kindergarten kids, know how to count time. Okay, but for us, we need to understand this: the incident and the reflect, they must happen together. Okay, because it's so short, they have to add together when you calculate the total voltage at this time. Okay, same as if you want to calculate the voltage. If you want to calculate the voltage at z equal to L, okay, it's the same thing, right? It's the same thing. So from 0 to 1, the wave hasn't reached the terminal yet, okay? Then this is 0, right? And then at the first t, right? At first t, I have to add this and this. I have to add, right? So that is 80, right? So after another, okay, this is first t, right? After another 2t, right? Go 1t, come back another t, 2t, you have to add, after 2t, you have to add this and this. Okay, this is a minus something. Minus something add on top of existing 80, right? So you reduce a certain amount. So that is this. So is that easy? That easy, right? Okay. Same as current. So I don't repeat. And then this is what we are looking at, the transient wave voltage and current at a location. Okay, we find the location, we find the transient waveforms. Okay, and now let's take a look at the transient voltage. Okay, the transient voltage at the time. Okay, the transient voltage at a certain time. Okay, at a certain time, the transient voltage at a certain time. At a certain time, which one is time axis? The time axis we said this is the time axis. This is time axis, right? This is in the unit of capital T, okay? Because capital T equal to total length divided by the wave speed, right? So we don't need to specify what the length, what the velocity. We just know total time travels. So this is total time, right? So if we interested in, okay, if we interested in, say, for example, 1t equal to this much. So in this case, the capital T equal to 1 microsecond, okay, microsecond. So if we like to observe, okay, if we like to observe at a certain time, what is the voltage across the transmission line, okay, across the transmission line. Then we draw, you see, because this is 2, right? This is 3. So 2.5 is between 2 and 3, right? So this is so we draw, this is our line. This is our line. Okay, this is our line. Then this is our distance, our location, right? We observe along this timeline, we observe at different locations. We observe at a different location, okay, to see what we can find the voltage, right? Okay, then at the beginning, okay, if I stand here, okay, so you see, because if I look at this diagram, we only have one dividing point. The dividing point is here. You see, because before this point and after this point, we have make difference, right? You see, because before this point, or one z less than, this is a half, okay? This is a half of the total length, okay? Half of the total length. Before this, at this time instant, we already received this voltage, 60. We also receive another voltage, which reflect 20. And we also receive this because this already happened before this time, 2.5 microsecond is before this time, right? Okay, this already happened. Then you add them together, no matter where you observe, which is the same. Okay, they all happen. So that is, you add together, that is 76. Okay, and after this dividing point, then this wave, the 1, 2, 3, this wave, so this wave hasn't reached to this dividing point yet, right? So therefore, at these locations, at this time, we only see this and this, right? We only see these two. So therefore, we only have a voltage 80. Okay, this is how we observe the transient response for at a one-time snapshot. Okay, snapshot. right? So this is what we discussed. You see, a very intuitive way to analyze the transient response. Okay, the transient response, and also from this simple example, we can see what is the transient analysis. One is a steady state. Okay, one is transient analysis. Okay, one is a steady state. One is a steady state, right? Steady state is at infinitely long time. After that, what happened to the circuit? So that it becomes steady. Okay, steady means okay, the derivative with time is, oh, sorry, I cannot say that. It depends on what kind of signal. If your signal is a sine omega t, even steady state, that is still a function of time. So derivative with time not equal to 0. It depends on what kind of excitation. Okay. For finite impulse or finite, you say, let's say the change with time, and then at the steady state, usually the derivative with time equal to 0. Okay. Then for steady state, how we look at the transmission line. Okay. For non-steady state transient analysis, okay, then we consider the reflection coefficient and for voltage reflection coefficient on both ends. We can use bounce diagram technique. We can find transient voltage and current either in terms of location or in terms of time. Okay, that's all for today. And if you like to discuss with me, for those students who leave a question, we can discuss right now.